Waiting for my slide. All right. Well, first, I just want to say what a pleasure it's been to be here, and I'm very humbled to be in this room with all of you. So thank you. As a review talk speaker, I was tasked with talking a little bit about the kind of public outreach side of things. So I'm going to start with a little bit of motivation before I jump into all of the JWST stuff. So really, really big picture, what I love about my work is that I think it fundamentally comes down to these two questions. Why are we here and are we alone? We've seen some pale blue dot images. This is the Cassini version of it. And we have heard about exoplanets and the search for, let's say a habitable Earth 2.0. But I think the challenge there is that it is a little bit of a needle in a haystack that we're looking for. So an alternative approach, I think, is to understand our origins. And of course, astronomers look at those bottom two steps in this process. And what people in this session are going to talk about is the origin of the Earth part of this. And I think the other thing that we try to do is, it's not a great strategy to just look at the Earth over and over again, but really what we want to do is understand all of the possible pathways that planet formation might take, successfully or unsuccessfully, and whether it might, result in an Earth-like planet or something totally different. Or something like Venus, which is very, very similar and yet uninhabitable. So the solar system's interesting because it does actually provide us some variety in the possible pathways. And we think the main ingredient that results in these different outcomes for the solar system is a temperature gradient, or alternatively, you can think of it as distance from the sun. And the reason for this is this kind of basic story that we tell ourselves, which says that if you combine this temperature gradient with volatility meaning the preference of a material for being in the gas versus the solid phase, you get different compositions. So for example, if you're close to the sun, only a few materials are solid, so that makes your Mercury. And as you get further away, this is not working, there we go. Earth has a few more materials, and then Jupiter, and then Neptune, and so on. And this story also has the nice characteristic, this is not moving forward, there we go, that it also might explain the difference in location between the terrestrial planets and the gas giants, because when water ice freezes out, that makes a lot of extra solids for you to form a planetary core, which can then attract a gas envelope. So the solar system, though, really only has this one axis, which is distance from the sun. And there may be many other axes to consider, and we've heard of some of them already this morning. So, we might think about stellar mass. Low mass stars are very abundant. So what happens to planet formation there? Metallicity might be important, and that can influence how early in the universe Earth-like planets might form. We heard this morning about radiation environment and how that matters. And it may be that maybe most planets actually form in massive clusters. Stellar multiplicity probably matters because most stars are born in binary or multiple systems. And then this is a little bit of a catch-all, but I think we do have to ask, can similar disks evolve into dissimilar planetary systems? So there might be some randomness in the process, or we can think of this as what's left after we've accounted for other axes. And then implicit in all of the studies that are going to be in this session is using the time axis. So the solar system is just the end result of planet formation, but what we can do is go back in time and watch the process as it happens. So let me tell you a little bit in particular about how JWST helps our field. So if we're wanting to study chemistry in planet-forming zones, what we do is use molecular spectroscopy, and we focus on protoplanetary disks. And for any non-experts here, those are just young solar systems. And this is what they look like. This is a little gallery of images from millimeter wave images from the ground. So you can think of this as the baby solar system out of which the planets eventually form. And if you want to do molecular spectroscopy, the way to do that is with MIRI MRS. It's really amazing. This is actually a pre-launch prediction of a spectrum. So it just kind of shows you some of the highlighted molecular features. Anything that's not labeled is actually water vapor. And one of the great things about MIRI MRS is that compared to past instruments, it has much higher spectral resolution. And I haven't heard anybody really talk about this, but what it does is it really deblends all of these features from the molecules, which is important for our analysis. So it's not just about identifying the molecules, but really doing more complex analysis. And then, of course, JWST is really sensitive, and that's what's allowing us to explore these different axes. We were really kind of stuck on one end of a lot of these axes when it came to Spitzer. Now, the main thrust of my talk is not going to be about spatial information, but I just want to say, because I do get asked, can you spatially resolve the disks? The answer is sort of. So JWST's resolution is about 30 AU for nearby disks. That's the distance of sort of Neptune. And so in general, we're not resolving chemistry, but we can see the broader context in which the planet formation is happening, including the material flowing from the disk onto the star. Well, we're not seeing that, but we're seeing a result of that, which is the outflow of materials in winds and jets. So let me just, I don't know if my finger's just not strong enough. Let me just jump right into JWST here. So, so we already saw the image on the left from Melissa McClure's Ice Age program, but just kind of gives you a sense of what's possible. This actually happens to be a HST JWST composite, but it's possible to take these kind of images with JWST. What we're seeing here is an edge on disk. So the black lane is the disk blocking the stellar light. The red is some light that makes it out. The blue is a collimated jet, and the green is a disk wind. So we can get these incredible images of the context. On the right is another example. This is from my team, JDisk. A really surprising result. We just looked at the images of H2 from a disk, and we see kind of a ring of material around the star. So we're not entirely sure what this is, but it's a more face-on system. So maybe if you turn your system on the left face on, maybe you would see something circular, a little unclear. My main point is that the amazing instrumentation of JWST gives us these images for free every time we take our spectra. So I think even though it's not the main thrust of my talk today, you're gonna see some amazing images coming out as well. So some of what we've been doing with JWST is really exploring this temperature distance axis that I told you about from the solar system. And so let me explain again. So the spectral resolution that MIRI MRS provides allows us to do pretty detailed analysis of the molecules. So this is just a small portion actually of a MRS spectrum, showing everything on here is basically water vapor. And so all the triangles are labeling some water vapor features. And there's a model and data. You can see it's pretty okay match. And the colors of the triangles tell you the excitation temperature of the lines. And the main point here is that there's a wide range of temperatures that the molecules are emitting at. And so you can back out where the molecules are. You can also figure out how many there are and things like that. So we get some pretty detailed information. It's not just, is the molecule there or is it not there? So we can really get direct measurements on this distance from the star axis. So on the left, you can see two examples where the researchers have measured the temperature versus distance from the star. And then we can compare that to models to see if we have the right idea about how this happens in other systems. On the right, you can see we can also measure molecular abundances and then try to plot those as a distance a distance from the star axis. So we can really kind of directly make the extrasolar version of our solar system story. So that's kind of the standard story, but there's a lot of wrinkles in this standard story that are super interesting and I think have been the focus of a lot of work in this field in the last few months. Here's just a beautiful composite that actually Klaus made of Miri-MRS spectra from our team. And what you can see here is just diversity seems to be the norm. So there's just an incredible diversity in what the spectra look like. And that includes, for those experts in the room, you can see the big bumps are the solid state features, but all of the tiny little lines are the molecular gas. And there's variability, not variability, diversity in that as well. And this doesn't really fit in the distance from the sun story, because if you have similar mass stars, you would expect, okay, their luminosity is the same, so temperature is the same. So what might be going on here? So this is a very editorialized version of what my reading of the recent literature. So you'll have to forgive me if you're an expert and you disagree, but I tried to summarize what I think are some of the growing themes that are bubbling up in this field. So I think one idea is that the chemical diversity comes from, I would call it maybe peeling back the onion, or maybe like carving out an onion. So if you imagine the distance from the star axis as providing a series of chemical rings, let's say, then let's say you're missing some material from the inner disk. It's now going to reveal different parts of your chemistry. And these rings could be, you could have large gaps, or you could even have rings. And, does this make sense? Well, if you go back to the images of protoplanetary disks, we now know that they're full of these rings and gaps. So it actually makes a lot of sense that we would see different parts of this onion. Another idea that is being talked about quite a bit is pebble drift. So the way pebble drift works is that in a canonical disk, you would have a pressure gradient that is such that it moves small solids inwards with time, actually pretty quickly. And these, what we call pebbles, carry icy materials from the outer disk. And when they get to the inner disk, they sublimate, so they enrich the inner disk in whatever they were carrying inwards. So for example, if you are bringing in water, ice-rich solids, then the inner disk gets enriched in oxygen. And because we like to talk about C to O, we often parameterize this as a C to O. So that would give you a low C to O ratio in the inner disk. But if your disk has substructures, that actually alters the pressure structure. And so the presence or absence of these substructures actually will determine what happens with the inner disk chemistry. So on the bottom, I show an example where, let's say you are trapping your water-rich solids, your water then does not travel in. So relatively speaking, you end up with oxygen-poor gas in the inner disk for a high C to O ratio. And you can see there with my horrible cartoon that one reason you might get these substructures is due to planet formation. So again, does this make sense? Well, disks are full of substructures, so it's definitely something we should be considering. So let's look at some actual data. So this is 3 spectra. These are actually all from the MINDS team. And for a non-expert, I have to apologize. I feel like we should settle on some color schemes. But I think the thing to look for here is blue is water, and other colors are other molecules, which are almost always carbon-bearing molecules. So if you see something with a lot of blue popping out, that's oxygen-rich, and something where the blue is more repressed, then that's oxygen-poor. So on the right side, we have low C to O ratios, on the left side, high C to O. And this is me editorializing about the interpretation of these results, but for high C to O, it was proposed that maybe there's a gap that's been revealed between the water and CO2 snow lines, which gives you a lot of carbon dioxide. So this is kind of a carving out the onion scenario. On the right, it's kind of interesting. So one of these sources has low C to O, and the author suggests that there was inward transport of oxygen-rich solids, so a pebble scenario. But then the other disk, they also kind of need to have a lot of oxygen, but this disk has substructures, so it should have stopped the oxygen from moving inwards. So they suggest that maybe the pebbles moved in the path. So this starts to get a little bit complicated, right? And so I'm really curious to see whether every disk is going to need its own unique story, which is a little bit unsatisfying. And so I'm really curious to see what sort of unified theories will emerge. And I think we're going to see this soon. There's at least two kind of overview papers that are in progress. There's also another approach to looking at pebble drift, which Andrea Bonsati will tell us about next. So I won't dwell on this except to tell you that he's going to tell you all about this beautiful figure here, which it might be a direct piece of evidence for pebble drift. The final thing I want to mention is just radiation effects. So this is something we actually learned from Spitzer. On the right is just a cartoon illustration of a disk with a very large dust gap. These disks are really interesting because although they have dust gaps, their dust gaps are full of gas, or at least they have gas in them. And I don't know if this is controversial to the solar system folks in the audience, but it's possible that this is a solar system analog, even though it's kind of an oddball amongst protoplanetary disks, because if Jupiter forms earlier, or it does form earlier than the terrestrial planets, so perhaps it actually carved a large gap in our solar system. So what happens in these types of disks is that then the inner part of the disk is more directly irradiated by the star. And that might be where an Earth-like planet is forming. So this is something we actually learned about a little bit with Spitzer. So this is not probably readable for a non-expert, so I'll walk you through it, but just on the bottom, you can see what a typical disk spectrum looked like with Spitzer. All of those bumps and wiggles are due to water vapor. So most disks were water vapor rich, but all of the disks that had these large gaps did not have water vapor in them. And again, that's a little hard to see for a non-expert, but on the top, those were basically noise spectra rather than water. And we've seen just a really dramatic demonstration of that with JWST as well. So on the top, that's a comparison of a molecule-rich disk on the top and one of these gap disks on the bottom. However, if you really zoom in on that bottom one, there's actually water vapor there. And if you look at the luminosity of the water vapor, that's what's shown on the bottom there. The luminosity for this source, PDS70, which is that blue dot, is a couple orders of magnitude below what was seen for all the black dots, which are all the Spitzer measurements. So we're actually, with JWST, we're so much more sensitive. That's something that we were really not able to see at all with Spitzer IRS, we can now measure. And it might be something that's really relevant for an Earth-like planet and its formation environment. There's also been some really interesting work on the stellar mass axis. So this incredible spectrum shows tons and tons of hydrocarbon-rich emission. This is a low mass star, an M dwarf, M4.75. And for the non-expert, what we're used to seeing are all the sharp spikes. What we're not used to seeing are the giant anthills. Those normally have not existed in our solar type stars. And me editorializing for what could be the cause of this, according to the authors, they essentially say, well, maybe it's a different kind of onion. So maybe the chemical structure is just a little bit different around this lower mass star. Maybe it's different type of pebble drift for this object, or maybe it's about the radiation field of this low mass star. And I think we're going to hear more about this maybe in Inga's talk. But what's really unusual is that my team observed another object with basically the same spectral type, so M5. And this one, it also has some hydrocarbons. It does not have any of those anthills. It just has regular, a pretty typical looking spectrum for someone who is used to looking at solar type stars. So, and it also has quite a bit of water. So what's going on? And this is an attempt by our team to put multiple axes basically on one plot. So what they're trying to do here is basically show a time axis and a mass axis and what I call the stochasticity axis all in one. So the idea here is for all disks, as you bring in your oxygen-rich solids, your C to O drops. It's been proposed that after that, there's actually a stage of bringing in carbon-rich material. So then your C to O rises back up. But that rate changes for different mass stars. So that's the red versus the blue. And then it all changes again if you have substructures in your disk, and it can change maybe in pretty complex ways. So they kind of draw that as a shaded region. So I think, the story can get a little bit complex. So again, I'm really curious to see what sort of broader themes we can pull out. So what's to come? This has a very short answer for you. We're going to be exploring all of these axes of planet formation. So this is not meant to be exhaustive, but just to show you that there are programs really exploring every one of these axes that I'm aware of. And also many submitted in Cycle 3. I'm obviously not aware of other people's proposals, but I know that I'm at least I'm working on 2 of these axes. Fingers crossed. So in conclusion, I think we need to investigate many dimensions of planet formation if we want to understand our origins. JWST's spectroscopic capabilities and sensitivity are allowing us to get chemical information from terrestrial planet-forming regions, but in a much wider range of types of environments than we did before. And what we've learned, I think, so far, most importantly, is that the spectra are diverse. And we do have the scenarios to produce that, but I think we're working towards a more unified picture. So expect a lot of insights on all these axes in the coming years. Thanks.